In this video, we're going to explore what differentiation means, how it's defined, and how we can interpret it both geometrically and physically. Differentiation is the process of finding the derivative of a function. In simple terms, the derivative measures the instantaneous rate of change of a function's output with respect to its input. Geometrically, it gives us the slope of the tangent line to a curve at any given point. Now, let's look at the formal definition of a derivative. For a function f of x, the derivative at a point x is defined as the limit of the difference quotient as h approaches 0. Specifically, f prime of x equals the limit as h approaches 0 of the quantity f of x plus h minus f of x, all divided by h. This fraction represents the slope of a secant line between 2 points on the curve. As h gets smaller and smaller, the secant line approaches the tangent line at point x. Let's see this more clearly. As h gets smaller, watch how the secant line, in orange, gets closer and closer to the tangent line, in red, at our point. When h becomes extremely small, approaching 0, the secant line essentially becomes the tangent line, and its slope equals the derivative at that point. Now, let's discuss the physical interpretation of derivatives. If a function represents position as a function of time, then the derivative gives us the instantaneous velocity. More generally, the derivative tells us how rapidly one quantity changes relative to another. This makes derivatives incredibly useful in physics, economics, engineering, and many other fields. There are several notations used for derivatives. F prime of x is the most common notation, where the prime symbol indicates a derivative. dy/dx is Leibniz notation, which emphasizes that the derivative shows how y changes with respect to x. And finally, d sub x of f is another notation, sometimes used in more advanced contexts. Now, let's look at some basic differentiation rules. The power rule says that the derivative of x raised to the power n equals n times x raised to the power n minus 1. The constant multiple rule tells us that the derivative of a constant times a function equals the constant times the derivative of the function. The sum rule states that the derivative of a sum equals the sum of the derivatives. We also have more complex rules for more complex operations. The product rule states that the derivative of a product of two functions equals the first function times the derivative of the second, plus the second function times the derivative of the first. And finally, the chain rule, which is used for composite functions. It states that the derivative of a composite function f of g of x equals the derivative of f at g of x times the derivative of g at x. Let's now see a simple step-by-step example of finding a derivative. Let's find the derivative of the function f of x equals x squared plus 3x. First, we identify that this is a sum of two terms x squared and 3x. Using the sum rule, we can find the derivative of each term separately and then add them. 4x squared. Using the power rule with n equals 2, the derivative is 2x. For 3x, we can use both the constant multiple rule and the power rule. 3x can be rewritten as 3 times x to the power 1. Using the power rule, the derivative of x is 1. Then using the constant multiple rule, we multiply by 3 to get 3. Therefore, the derivative of x squared plus 3x equals 2x plus 3. To summarize what we've learned about differentiation, it's the process of finding the derivative of a function, which measures the instantaneous rate of change. Geometrically, it gives us the slope of the tangent line to a curve. Physically, it tells us how one quantity changes with respect to another, like velocity is the derivative of position with respect to time. We have various rules to help us find derivatives efficiently, including the power rule, sum rule, product rule, and chain rule. Differentiation is one of the two fundamental operations in calculus, along with integration. Understanding differentiation opens the door to analyzing rates of change throughout science, engineering, economics, and many other fields.